Hello, everyone. Welcome back to a 450 quick example problems to prepare us further in the world of thermodynamics. So let's start with an example on equilibrium type problem. So equilibrium problems are vast and have a lot of applications, but in this class 450, we're going to focus on the dissociation of CO2 to CO and O2 because that is a classical mechanical engineering application when we're burning fuels and concerned about what happens over time. Okay, so for this equilibrium problem, we're going to say state 1 of this equilibrium mixture is a mixture of CO and O2 at equal mole proportions. So it's not that there's 1 mole of CO and 1 mole of O2. They can be, but we don't know. It's like 5 to 5 or 10 to 10, 1 to 1. They're both equal mole proportions. And it's T equals 3000 Kelvin in this chamber. So that's a closed chamber containing CO and O2. And what we're going to do is say that, okay, let's say state 2 is at chemical equilibrium. And you have to know something about the chemistry in terms of equilibrium chemistry. So that's where it's nice for us to just focus on this one because there's just an infinite amount of different equilibrium processes in real life in many chemical systems. But we're just going to focus on whenever you have CO and O2, and we're concerned about some equilibrium at high temperatures as combustion takes place in, it's going to be CO2, CO, O2 system. Okay, so that's state 2. And state 2 is a chemical equilibrium. Also, given, as I just said, it's going to be an equilibrium mixture at the end of mixture at chemical equilibrium at 3000 Kelvin. And let's say, well, at pressure P. It's general at the beginning, but we're going to simplify it to 1 atmosphere eventually, but let's just leave that in there for now. Okay, so the general thing is when you have a chemical equilibrium problem, you have to know something about the behavior of these molecules. So thankfully for us in mechanical engineering, the most classic one is you have CO2 and at high temperature, it dissociates into CO and oxygen. Okay, so that's the general strategy for equilibrium problems. First, define the physical equilibrium reaction. Then it's not the same thing, but you have to define another reaction. So you have to know something about the equilibrium behavior of these molecules, which is not the same thing as a second reaction. So you have to define a second useful mass balance reaction. So in this useful mass balance reaction, it's different. So this useful one includes initial reactants and includes all product components, often all components do not participate in this equilibrium constant, only total moles. It's in there only because you have to find the mole fractions in many cases. And see, when we're talking about this CO2 dissociation, it's only these three things that are participating in the CO2 dissociation. But depending on the problem, you can maybe have water and like other details you might want to consider, or nitrogen. If there's from the air, you have nitrogen, water, nitrogen. They might have this contributions to the total moles, but they're not part of the ratio of the mole fractions here. So this is a different reaction. It's useful because you can keep track of everything, but it's not the equilibrium process that we have to define separately. Okay. So in our typical mechanical engineering applications, we apply this to CO2 dissociation, which is, you say CO2 has this equilibrium depending on the temperature. This we quantify it by this equilibrium constant. And what happens is, depending on the details, it's a mixture containing CO2, CO, and O2. And depending on the situation, you'll have a different proportions of these at equilibrium, at chemical equilibrium. So that's the equilibrium, chemical equilibrium model. And then once we define this equilibrium model, we can define our equilibrium constant, which is the ratio of the products multiplied to each other, raised to their coefficient. And then you have this pressure effect. Oh, this pressure effect is, in this case, the products, it's raised to the 1, plus it's raised to the 1/2, and then the denominator, it's raised to the 1/2 in the denominator, so that's a minus. So that becomes a 1/2 on the pressure effect. So depending on the pressure relative to 1 atmosphere, that's what this knot means, you can have an additional perturbation, not to the constant. This number stays the same at whatever the temperature is, this K will stay at a fixed number, but at different pressures, this will perturb the distribution. All of this whole, all of these here will have to rearrange themselves to get the KP the same. Okay, so that's the equilibrium part. Let's go to say that, okay, now we have to find a way to take into account the starting mixture and whatever products are in the end. So here we don't have nitrogen and we're not considering water. It's just simply saying that we start off with CO and O2. And CO is a fuel as well. You can burn it. And in the product mixture, it might, in real life, there is some finite equilibrium process. So we'll write this reaction here to account for the fact that, okay, in this case, it's straightforward that CO is the fuel. And we say that it's 1 mole, 1-to-1 ratio. It doesn't have to be 1-to-1, but we can start off that way to simply say that for every 1 mole of fuel, there's 1 mole of oxygen in the mixture, just the way that we define this problem initial condition, state 1. But it's going to form due to equilibrium that in the final product mixture, there's going to be some finite unknown fraction going into CO2, and then whatever CO2 is formed, there's going to be a proportion of CO. So this is the split between CO and CO2 according to X, and then another unknown variable. We don't know how much O2 is going to be left over. So but setting it up this way is a molar split between CO and CO2. That's what we did there. Okay, then we can use atomic balances, element balances, to try to narrow down the variables. So for carbon atom, on the left side, we have 1 carbon atom per CO. It's CO, so there's only 1 carbon in there, so it's 1. Then on the right side, there's going to be some X amount times 1 of carbon in CO2. Then there has to be some 1 minus X amount in CO, in the CO molecule. So that means 1 equals 1 plus 1 minus X equals 1. That doesn't give us much. It just verifies that, sorry, this should be X. That doesn't give us much, but it's nice to verify, because we could have, if we would have, that would have helped us to narrow this down beforehand without, if we did find it as like this as A, this as gamma or something like that, that would have, this carbon balance would have helped to narrow this down. The oxygen balance will help us to narrow down. Let's see, oxygen atom. So on the left side of this, oxygen atom is both in the CO and in the O2. So there is 1 molecule of oxygen and 1 mole of CO. So that's 1 times 1 atoms of CO, plus in the O2 molecule, there's 2 atoms and 1 mole of O2. That's the left side. That has to balance with this CO2 starting off. There's 2 atoms of CO and oxygen in CO2, so 2, and then there's X moles. 1 in the CO times 1 minus X moles, and then 2 atoms of oxygen and beta moles of O2. Okay, so let's start simplifying that. That means 3 here on the left side equals 2X plus 1 minus X plus 2 beta. Okay, so we can bring this here. 2 equals x plus 2 beta. So that means beta equals 2 minus x over 2. So we reduce the variables. We only have x now because x, beta depends on x. We found the relationship there, so we can now only worry about x. Okay, now that helps because we need to eventually find the mole fractions of this mixture to get the equilibrium, or to use the equilibrium constant, because we want to find the equilibrium mixture. So that will give you the equilibrium mixture will be expressed in terms of mole fractions. So to find the mole fractions, you need to find the moles in this mixture. These are all moles. And you need to find the mole fraction. Well, how do you find the mole fraction? You find the total moles of the mixture as a starting point. Total moles equals x moles of CO2, 1 minus x moles of CO, and beta moles of O2. We just found that, so we can say express this all in terms of x. That's what we just found here. And simplifying that, n total, 4 minus x. So, okay, that's the total moles. So we can find the mole fraction from each of these here. CO2 is x, 1 minus x is CO, beta is O2, which we found as this. So the mole fraction of CO2 equals 2, because this is in the denominator that goes up to the numerator, 2 times x over 4 minus x, CO, oops, CO, 2 times 1 minus x over 4 minus x, and y of O2 equals so those are the mole fractions. And then plugging that into this equilibrium constant for this specific CO2 dissociation. And we already know the temperature, so I'll plug this in as well. I mean, I'll just note this down here. The Kp at 3000 Kelvin equals, this is at the bottom. So let's start with this one here. It will be 2 times 1 minus x over 4 minus x times 2 minus x over 4 minus x to the 1/2. And then this is going to be in the denominator, so it would be 4 minus x over 2x, and then there's a pressure effect. Okay, so these cancel out, blah, blah, blah. So Kp at 3000 Kelvin equals, we simplify it a little bit, 1 minus x over x. And then this one square root term here, 1/2. So that would be Kp. Okay. Then many times for these problems, we have to use the tables or this Gibbs free energy equation. So in this case, we're just going to go to the tables. Because we already have X, we already have the temperature. Because we already have the temperature, we don't need to use the first law as another tool to find the temperature. And we don't really need to go to the Gibbs free energy tables either, because if we're only trying to find, I didn't specify here that what I should have said here is question, find equilibrium concentrations or mixture concentrations. That's what we're trying to do. So a useful thing is to go to the tables for K for CO2 dissociation. .32724. So that's in the table, A27. Okay. And then for P equals 1 ATM, P over P naught to the 1/2 equals 1. So let's just say for 3000 Kelvin, 1 ATM, that will set up our problem. That would be 0.32724 equals this expression we just had here. This is 1 now because it's 1 atmosphere. If it was a different pressure, there would be an effect there, but it'll affect the X, the final X that we get. But what I did, so this is a pretty nasty nonlinear equation here, but we're good with our calculators, or we have some solvers. What I did on Excel pretty quickly was I said 0.32724 times X times 4 minus X to the 1/2 equals 1 minus X. So when left-hand side equals right-hand side, or left-hand side minus right-hand side equals 0 at X equals 0.6595. So I found that, and then plugging back into these here will give you the answer for the equilibrium concentration. So Y equals, I'll just repeat one of them for quickly, 2x over 4 minus x equals 0.4-ish. To Y02 equals 0.4 at 3000 Kelvin equilibrium, P equals 1 ATM. This is all the equilibrium components, concentrations. All right. So I'm going to pause this one and come back with another example, and email me with further questions.